Hello everyone, we're starting the meeting. Hello, come and take a seat. Hey. Oh. Well, yep, let's start the meeting now. Now that we have everything ready. So welcome everyone to our January body meeting 5 of the semester. Yay. Attendance is at acm@uc.org/. It's really important so we know how's our attendance going. Some introductory slides. What is ACM UC? We are the student chapter of Association of Computing Machinery, with the computer science and programming coding community at UC. We try to be a group of students that is built around a common interest in technology, computer, and software, with helping out each other. And any majors are welcome as long as you have an interest in technology. You can all come and join us. Our official mission is to encourage professionalism among tech enthusiasts in a collaborative fashion by facilitating learning beyond the scope of classroom to develop innovative and inclusive ideas. We do that through a variety of ways, like event guest speaker. For example, today is Professor Hawkins. We also do it through the ICPC or our own hackathon, Revolution UC. We also have a Discord community and office hour. So the membership requirement is attend 2 meetings and remember to check in, record your attendance, and that's it. You don't have to pay for ACM Nationals, and at the end of the year, you'll be able to vote if you are a member. Code of conduct, ACM is dedicated to a harassment-free experience. Our anti-harassment policy can be found on our website. We also follow UC Code of Conduct, including any anti-harassment statement. Again, for the ICPC, it's the regional media programming competition that we help organizing. Registration info is to be announced. Discord, if you have not already, please join our Discord. We love Discord. Oh, that's not Discord. It's the best way to connect with us and with other people interested in technology. Like we have amazing people like Brandon, Pierce. We have a lot of channels: homework help, random opportunity for posting job posts, or like career help, where you can get resume help from us too. Other resources is our archive. Please remember to join our campus link so you get added to the listserv for up-to-date emails. And with that, I welcome Professor Hawkins, who's been like my favorite professor here at UC. He's been talking about the difference in speed between row major and column major ordering. Before that, I would welcome anyone to take a pizza. Here we have plates and napkins. I don't know if the email will say Domino's, but unforeseen circumstances force us to use everything.
Well, isn't Adriatico's better? I mean, ostensibly, right? It's supposed to be better, yeah. I know some people like Domino's though, so.
Here's the pizza. Please come in and grab slices. Oh, we have plates here too.
Do you want me to join the presentation? So I can.
Yeah.
Do you want me to do that? Yeah. Sure. Yeah.
Join.
Yeah. I think I'm on your Discord. Let me see. Is the meeting link on the website?
Yes.
The Zoom link. Okay.
So now Discord
Well, edu.
is .org. Website.
Click here to check in. Oh, that's
Oh, okay.
me see.
I can send you. I can forward
Do you
it.
mind? Yeah, because apparently I'm not. I'm on the IEEE one, but I'm not at ACM UC.
Okay, okay.
Yet, I will be though, I promise. Promise.
Forward to. What email do you use?
Oh, you can do Hawkins or HAWKI, yeah, that one.
Yeah.
Yep, perfect. Thanks.
And yeah, it will have the Teams link there.
Okay, perfect. There you go. Got it. Cool. I'm gonna mute my. Got it. Good.
Let me check to see if it works.
Let me share it here. I'll see.
Can you?
Yeah, that's the one I wanted. That's the button I wanted. There we go.
We're not seeing you on the screen. I don't know why.
It's working now.
That's a couple.
We see it.
Yeah. What do
So you
mean?
might need to, did I use the wrong one?
Yeah.
Okay.
There's two. I just
Okay.
like.
Yeah, that's fine.
Hopefully this one works.
There you go. Cool.
Does it? Oh no, it's not showing.
It registered that I was presenting. Let's try this one. Let's go back to this one.
Does it not work?
There you go. It found it. It just found something. So let's see. Windows said it found something. There we go. Yeah.
Okay, it's on the screen now. Yeah.
But hold on. But they still don't see me on the. It still doesn't look like they see me on the meeting.
If you just,
Yeah. No. I meant my slides. Like I was sharing my screen, so I didn't know if they should be able to see my screen.
okay.
Let me hold on. Let me try again. Maybe I didn't share it correctly.
I think they see your screen.
Okay. All right.
Yeah.
That's fine. Okay. All right. Cool.
Can you guys see the screen? For people online, can you guys see the screen being shared?
Yeah.
Yeah, I can see it.
Yes, they can see the screen.
Cool.
Hello? How does work? Maybe it doesn't.
All right. So tonight, this was so much fun to put together. So I'm going to share with you some stuff that I found. And what's really cool about this stuff is that the stuff that we're going to talk about tonight can be used for all sorts of fun stuff. Like you can use this information, and one of the ways you can use the code that I had to write for this was you can use it to exploit. Does everybody remember Spectre and Meltdown? The side channel attacks that they were used? Well, you can use the code here to detect and exploit those bugs. This is pretty cool. So the title was what I started to talk about, or what I thought I was going to talk about. And then I got distracted and went further. And so we're going to talk about more than that. We're going to talk about that sort of like as a kickoff to what we're going to talk about. So here's all my gimmicky art. I'm sure you get the joke, but okay, there it is. All right, so let's first start by talking about this. This is a really simplified view of what your computer is. It's two things. It's a processor and memory, and that's it. The processor doesn't have, we'll say for right now, doesn't have any memory on it at all. We know that it kind of does. It has little bits of memory. And to be able to get things into that little bit of memory so that it can operate on them, it needs to get them from memory, right? It needs to get them from RAM, somewhere out there. So let's say we wanted to do this. And our instruction says, okay, I want to load 4 bytes. Let's say our register there, R1, holds 4 bytes of data, some number. And I want to pull that in for memory. That's what that instruction does. And put it in R1. Well, the CPU is going to say, okay, fine. The first thing I need to do is go out and ask the CPU or ask the memory, get me the 4 bytes at that address. And the memory is going to say, okay, fine. Here's the 4 bytes. They're at this address. Then our CPU can actually do some operation on it. Big processing, right? It's just going to add 1 to it. We're really doing sophisticated stuff. And then I want to put it back. So our CPU is going to say again, okay, store that back to that, put this value in those bytes, and we're happy, right? Pretty cool. Can anyone see a downside to doing that? Can anybody see a downside to doing that? Yeah, latency. Good. Why latency? Or where latency? Sure. Yeah. Yeah, absolutely. Say again?
Clock cycles.
Clock cycles. That's right. Yeah. Exactly. Yeah. Good. How would you make it faster? How could you make it faster? What could you think of? There's a couple ways. We could make time go faster. Put them closer. That's good. I like that idea. What else? What else seems like a waste? You've written programs before, right? If you asked for some bytes at a particular address, what are you likely to do next? You're going to use them, right? But after you use those bytes, what are you going to do next usually? So I asked for bytes 501A, 501B, 501C, and 501D, right? Let's say that's the address of some variable in your program, some local variable, right? What's the next thing that you're going to do? Usually. Do you only usually have one variable that's local?
No, callback again, we use it in different part of the program.
It's used in a different part of the program, yeah. And what might you do with a variable that's right next to it? Like you've declared 2 local variables, right? For your function.
I also use both of them.
Yeah, you might use both of them, right? And if you have another local variable, you might use that one next, right? So what if those are all together in memory, right next to each other? What if all your local variables are back to back to back to back in memory? Could you do anything better than this? Anything better than this? Yeah. Yeah. Why am I just going to get you those 4 bytes? Why don't I get you a bunch of bytes? I'll get you those 4, but I'll also get you some other ones too. So that way, if you ask me about something next to it, I've already got it ready for you. That'd be pretty cool. So we're going to do both. We're going to put it closer to you, and we're going to get a bunch more stuff. Okay? So now, when we ask, give me those 4 bytes, I'm still going to ask, hey, give me those 4 bytes. But now I'm going to put this thing in the middle, and it's the cache. So instead of just returning those bytes directly to the CPU, we're going to send them to the cache first. And not only are we going to send those 4 bytes to the cache, we're going to send 64 bytes that are around that. We'll talk about why 64 bytes in a second, but we'll just say 64 bytes. So now those are in the cache, and then goes back to the CPU and we can do our operation, right? But we need to change our diagram a little bit now, or else this whole thing was kind of useless, right? We need to change it because when I load, now I need to ask the cache first. And if it's not in the cache, then what happens? Right. I asked you the wrong question, I'm sorry. When it is in the cache, what happens? I forgot the order of my animation. Exactly, the cache just says, here it is, right here. That's much faster, right? I mean, presumably. We'll talk about why it is. And if it's not there though, we do have to go back to here, and then we have to go here, and then finally we can return. Okay. So what's cool is now I'm going to ask for the next 4 bytes after I loaded that first one. And this is awesome because now I'm here and you gave me those 64 bytes that are next to it. So I can just go bloop, much faster, right? Or is it faster? Like why, if that's faster or what, like, okay, so I'm telling you that's faster. Well, then why not just make the memory faster? Okay, well, anybody think about why? Why don't we just make the memory faster? Yeah. What's the trade-off? What's the graph? Like, how does that work? Cost, speed, size. What do you think? Huh? Well, I don't know if it's exponential, but like when what goes up, what else goes up? Yeah, as speed goes up, costs more. As size goes up, if you want to keep the speed up, more money, right? Like when you buy an SSD, no one I know does this anymore, but if you bought a 1 terabyte SSD or a 2 terabyte SSD, and you bought a 1 terabyte 7,200 RPM drive, or I guess they're even 15,400 now, whatever they are. Like one costs like $1, right? I mean, you can get those really cheap, the spinning drive, but the SSD is still, it's not cheap, right? Like when you bought yours, when you bought your MacBook, it was probably like, okay, you want 1 terabyte drive or 2 terabytes? And it was like, I mean, I'm gonna buy the 2, but it's more than I want to pay. But if you go from like a 1 terabyte spinning drive, we don't have to pay for the speed because it's still slow. So what do you think about the sizes of these two things? What do you think about the sizes of these two things? Do you think that the cache is smaller than the memory? Yeah. Yeah. What's amazing though is like how big and fast the caches actually are these days. I'm surprised by that. Has anyone looked at the specs on their CPU recently for how big the cache is? Yeah, I mean, it's getting like really big. Now, the problem is, what's really interesting about that is the next slide. I'll tell you what I think is interesting about that next. Okay. So that's a nice, simple version of the cache. And we'll go with that. Like that's a really helpful model to think about how things work to write our code. But what happens is actually a little bit cooler. There's actually levels to the cache. So we have the CPU all the way down here. And then we have this cache that's right above it. And it's small, but it's really fast. Really, really fast. Then there's a cache above it. And it's bigger, but still small. And then we have memory. Usually what happens is that they're like subsets of one another. That doesn't have to be the way it is. Like a CPU person could design their processor however they wanted, but that's usually how it works. They're like subsets. So what I think is so funny, when they advertise when the chip maker advertises their cache size, they're usually talking about, and there's usually 3 levels these days on chips. So they usually tell you what the level 3 cache size is, which, I mean, it's giant, but doesn't really get you much. In fact, that's one of the things I wanted to explore, and we're going to talk about tonight. So how does this work? Well, let's do this. So when my CPU asks for a particular piece of memory, get me the 4 bytes at 501A, it's not going to get just those 4 bytes. It wants to try to fill up a section. This is just a section of the level 1 cache, right? It doesn't want to just get you those. It wants to get you them around it. And we said that was 64 bytes. That could be any number, but it's usually 64 bytes on chips today. And that matters because the chip communication with the cache, with the RAM, is all optimized to go along these certain data paths. And they want to start at a certain kind of address and end at a certain kind of address. So I can't just say, get me 501A and the next 64 bytes. Like, that's not fast. It's fast, though, if I get them along 64-byte boundaries. So the first thing that the cache does is say, okay, I'm not going to get you 501A and the next 64 bytes. I'm going to find out which 64-byte chunk I'm in the middle of and get you those 64 bytes around it. So in this case, I'm going to get you 5,000 to 5040. And my 501A is going to be somewhere in the middle. But the level 1 cache says I don't have that, right? So then it's going to ask the level 2 cache, do you have it? Do you have anything between this and this? There's an unfortunate typo here, and I'm going to fix it. Who can multiply 64? I guess that'd be, what's 128 in hex? Is it 80? I think it is. You'll see why I'm mad at myself in just a second. I know, right? And now you'll see how I struggle with PowerPoint. Yeah, it's like, there we go. There we go. Okay. Well, we said the second level cache is bigger, right? So instead of just getting the next 64 bytes, let's be more aggressive. Let's get 128 bytes. We'll bring it, we'll bring it closer, okay? Well, I'm still stuck because my layer 2 cache doesn't have that in it, right? So we have to go out to memory. But that's okay. So we're going to come back in, but we're going to come back in a really interesting way. We're going to prioritize those first 64 bytes because those are the ones we really want to bring as close as we can. So I'm going to bring in the first 64 bytes. Yes, that's totally random. I literally hit random keys on my keyboard. So it ends up there first. Then it gets in here. And then the 4 bytes comes back. That's pretty cool. Sometime later, though, and pretty quickly thereafter, the rest of this gets filled up. with the other 128 bytes. So then if I boom, 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 all 64 bytes in that row or in that line, then I start going to the 65th one. Well, now I don't have to go all the way out to RAM because it's right there in the L2. And it's bigger, so I can be a little more aggressive with my optimization. Pretty cool. So I wanted to know, can you actually detect this? Like, can you detect the way this works and see how it works? Or, as a related question, can you probe and see how big your line size is? Like, if you didn't have a data sheet for your CPU, could you figure this out by writing code to do it? And that's what I wanted to find out. I think we can. I think we can. So does everybody understand what I'm trying, or what we have here, and what I'm trying to do? Who wishes they just took the pizza and left? Yeah, you're all like, wow, I signed up for a talk about CPUs tonight?
So you want to detect it to different times, it gets you out.
Yeah.
Like really fast.
Yeah. Yeah, you got to really be very careful. So let's start with this little example. There are two people in here who might cheat, so they're not allowed to cheat. But let's say I have a two-dimensional array. We've all seen two-dimensional arrays because we've all used pandas before. And this is great. I love two-dimensional arrays. But is our memory two-dimensional? No, not two-dimensional. So I've got to somehow put this two-dimensional thing in a one-dimensional space, right? How can I do that? How can I do that? Ooh, okay. Well, hold on. Don't steal. Don't steal. Good. So what was your first suggestion? Take the rows and put them side by side. Okay. So this is going to be, I'm going to go this way, right? So I'm going to go this way. Okay. And then I'm going to go this way and this way, right? So if I'm looking at these cells in order, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Good. What's the other way? I'll even change colors. Yeah, exactly. So this is still 1, but now this one's 2, this one's 3, this one's 4, 5. Well, that's interesting. 6, 7, 8, 9. That was me being genuinely surprised, by the way. That was not like pedagogical. I never realized that all along the row there, or along the diagonal, they were the same. That's pretty cool. All right, so if we do that, then these are our two orders. We have A1 that goes first, A2 that goes next, A3 that goes next, B1, B2, B3, C1, C2, C3 up on the top, right? That's when we do row, row, row. Your boat gently down the street. Yeah, I know. Then the other one is column, 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 right? Okay. For this example, or for our code that we're going to use to test, we're going to assume that our two-dimensional arrays are laid out in the first order. in the first way. So it's row, 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 okay? Based on what I just told you, I want to know if there's a difference in these two loops. I mean, they're doing the same thing, right? They're nested. I get to operate on one element, each and every element.
But the other one, a grand particle compared.
Okay, why?
Because of how the CPU manages the bits.
Exactly. If I ask for this element right here, what else is the CPU going to bring into memory? A2 and maybe A3, maybe A4, maybe A5, right? Because they're the next in order in memory. So I ask one time and I get all this back, right? So if the next thing that I ask for in my loop is A2, it's already going to be there. And then if the next thing I ask for is A3, it's already going to be there. If I did it the other way around though, if instead of asking for A2 next, I asked for B1 next, I'd be out of luck, wouldn't I? I'd have to go all the way out to memory, bring it all the way back in. So here's the question. That seems like it's going to make a difference, right? But does it? Do you think it actually does? You seem very confident. Have you seen this before?
Maybe.
Yeah, maybe. The absolute numbers on the side don't really matter. But that's a pretty big difference, isn't it? Pretty big difference. So yeah, it really does matter. Our CPU really does this and will really help you. So if you write code, it helps to know how your data is laid out in memory, because you could write the really slow one on top, or you could write the really fast one on the bottom. And the difference in the code is like little effort, right? You just have to know how to write it. Do I loop through the rows first and then the columns, or the columns and the rows? So now I wanted to know something else might matter, right? If I have 64 bytes that I get at a time, and I run this code, whoops. These are integers in the array, right? An integer is like, let's say it's 4 bytes. Doesn't matter what it is, it's 4 bytes. So if I ask for one integer and you get 64 bytes back, I get, how many integers is that? 16? 16? 16? So that means the next 16 memory fetches are free, essentially, right? Now, what if the element in my array is now, instead of 4 bytes, it's 8 bytes? I get 8 for free, right? The next 8 accesses are free. And what if it's 16? It's 4, right? So every time I make the element in my array bigger, I get less advantage, right? Because it's bringing in fewer items, right? Eventually, when I get to the size of the line, they should be the same. Because the next element is going to be a new fetch. the next element's going to be a new fetch. The next element's going to be a new fetch, right? So there should be some crossover point. It should look like this. It should look like a line like this. A lot of speed up, no speed up. That literally hit me in the middle of the night. Don't ask me why I was thinking about this in the middle of the night. And I thought, oh my gosh, wouldn't it, like, that makes sense in your mind, right? I thought, wow, that's the way it should work. I wonder if it actually does. You now are like totally against me. You were with me now. You're like, no, that's not how that's going to work. So let's look at it. So no more slides. The rest we're going to look at code. And this is all on GitHub, so you can see all of it if you're interested. I can't run any of it on my laptop. I have it on my desktop. So if you want, we can look at that. But I wrote a little program. And all it does is when I compile it, I give it this value of X. And this value of X is going to make this element some number of bytes long. And that's going to be what's in my array. Okay? Then, in like the ultimate low techness, I just compile a bunch of different versions of the code. So I have loop speed 8, loop speed 16, loop speed 24, loop speed 32, 40, 48, 56, and 64. Each version of the program has an element that's that big, right? We're not going to do 4 because we already did 4 basically. We saw it was a pretty big difference, right? So I ran those in the same way that I did before. You can see all I did was I did 2 versions of it. One was row, one was column, but the array was exactly the same, right? It was just a certain size. And then I could see, okay, which one was faster? You ready? Okay. Notice where we started to cross over. Yeah. Look where we got really close to no improvement. What do you notice about that number? See the 64? 64. Yeah. So I went all the way up to 128. I'm surprised. This really surprised me. First of all, I was blown away that like what makes sense in your mind, like you could write code and actually see it. This is exactly what we expected, right? We got less and less advantage the fewer free reads that we got. So I got a bunch of free reads on the left, all the way down to like, basically no free reads on the right. But then what surprised me, I kind of expected it to go flat after that. But it just keeps like descending into hell. And now all the way on the right, it's like, oh, please don't do it like that, right? It almost like do it the other way now. So since I know you were coming for homework, you can think about why that happens. I don't have the answer. I haven't thought about it. I'm sure it makes sense, but I haven't thought about it. So think about it. Yeah, I mean, I don't know. It's almost like when it gets to be that, it interferes with, like it's knocking something else out of the cache, which is something we haven't talked about, but we can if you have interest. So. Yeah, I think that's what's happening. Yeah.
So are you saying that 64 is the size of the smallest cache?
That's my guess now. That's my guess. Isn't it yours? But don't worry, we're not done. We have another way to test if this is actually the case. All right, so that's interesting. So we're on the right track. And full disclosure, I wrote this and generated this graph after I wrote and generated the next one. So besides being able to read my data sheet, I knew it was 64, right? So I was pleased to see the line go down, but not surprised. All right. Let's think about this. Let's say in my diagram here, let's say I wanted to figure out where I dropped off between the two. What could I do? I'll give you a hint. Let's start by fetching the byte at 5,000. So if I fetch the byte at 5,000 and then did what next? What would the next thing I could do? I want to figure out how big that thing is. And remember, I can time things. I can time things. Yeah, for which one? Yeah, right. So why don't I do this? I'll ask for byte one, the 0th byte at 5,000. What should that do? Yeah, it should bring in the next, how many bytes? 64 bytes, right? Okay. So then, if I fetch 5,001, it should be fast. If I fetch 5,002, it should be fast. If I fetch 5,003, it should be fast, right? 4, 5, blah, 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 blah. And then when I get to 5041, what should happen? Should be slow, right? Because I'm outside of what I got for free. So why can't I do that? I'm just going to keep probing. Fetch the 0th one, probe. Reset, fetch the 0th one, probe again. Fetch the 0th one, probe again. That'd be pretty cool. I wonder if I could see that, right? The answer is you can. Pretty cool. Now, the problem with this code is it's not the most straightforward. Yeah, that's not straightforward. But the point is, I want to be very clear. You can understand this. It's not complicated. This literally, what I'm doing here is what I just told you. The rest of that crap is just kicking the CPU. The CPU is really smart. That's the problem. I mean, it's really smart. So why can't I just say, okay, give me byte 5,000, give me byte 5,001, give me byte 5,000, give me byte 5,002, 5,000, 5,003. The CPU is so smart, and this is baffling, that it will sense that you're doing incremental reads, and then it will start prefetching for you. I know, right? Like, and you can't even say, okay, I want 5,000, then I want 5,004, then I want 5,008, then I want 12. You know why? It recognizes that you're striding in the same distance over and over again, and it'll get you 5,016. I'm not kidding you. That's how smart these chips are. So, well, that's this code up here on line 29. That's the code on line 29. Now, what that is it's like a special instantiation of the block cipher code for 255. So this only works for values up to 255. But if you iterate from 0 to 255 and run it through that in some non-normal order, it will get you all those values. Not in 0 to 255, but full disclosure, I did not come up with that. You know where it came from? The original Spectre meltdown exploitation. So you have to do the same thing. All right.
Just curious.
Yeah.
You said the computers are so smart. I assume the compiler would just like
That's oh.
line 33 out.
Don't you worry. Don't you worry. Yeah. Most of the other stuff up there where I've got the word volatile is to tell the compiler, don't get rid of this. If you put volatile on things in C++, it says, whatever I write something or read to that thing, it must go. You cannot optimize it. So that's the first kick. The second kick is maybe I want these things to be stored always in registers so that they don't go to memory. Because if I'm trying to tie memory and everything and something else goes to memory, now I'm timing something else. So we sometimes need it in registers. So here's what we do. Every time we go through, we flush that line of cache. So every time we go through our probe, we take that away and we start again. We get the 0th byte, ask it to pull in the next one, because we don't want to take advantage of it, right? We just want to be fresh every time. So that's what this line does. That's what these two lines here do. You flush your base value, and then you flush the last one you just probed. This next line is there to let the cache fill up. Because even though it's fast, it's not instant. So we have to let the cache fill. So let's let the cache fill up a little bit. And then this is where we make our money. Right here. The RDTSCP is a little thing on the CPU that gets you a clock cycle count. This is like the most precise timer you can ask for from the CPU. So I want to know the cycle count before I do my read and the cycle count I do after my read. And notice, nothing else is inside of there. That's all that there is. So I'm literally timing just that. I've already even calculated the address that I want to read from. So unfortunately, you also have to look at the machine code that's generated to make sure that this is doing, because you're exactly right. The compiler is really tricky. I don't have the object code downloaded, but I could get it if anyone's interested after we're done. And then I store the answers and then print them out so I can graph them. We can do what they do on TV and cut to the chase because I have a graph and it's pretty pictures. Do you want to see it? Yeah. Who thinks it worked? I know you don't. You do. You do. Yeah, you do. Now the real question is, the picture I'm going to show you, does the picture I'm going to show you work? And what about the 2 days before that when it didn't work? No, I don't know what that one spike is. So don't ask. What do you notice? But where's the first hump? Where's the second hump? Think in factors of 2. 128. And then where does it go to hell in a handcart? Everywhere after that. So what can you detect out of this? What do you think my CPU is? What's the line size for L1 cache? And what's the line size for L2 cache? 28. Isn't that awesome? I mean, it's crazy. It's crazy. And what I think is also really interesting is look at this. Look how consistent this is for L1 cache, right? And look at how it starts to get a little more jagged at L2. The jitter on that's a little bit slow. Like, not only is it slower, it's a little more variable. And then look when you go to RAM. It's really jagged, right? I think that's interesting. So not only is it slower, there's more variability in it. I'm sorry? I still didn't hear you. I'm sorry. Oh, yeah, absolutely. Yeah. So that might be L3 up there. To be honest with you, that could be L3. I didn't look on my spec sheet to see if my CPU is old on my workstation, and it's a workstation CPU, so it might not even have L3. It's a Xeon from a few years ago. There's 4 of them, but it's still old. Yeah. So that was my journey, and I thought it was pretty cool, and I want to tell you all about it. So there you go. Now, what's cool is Inspector and Meltdown, they actually used this difference. They used this hump right here and this hump right here to detect and read memory. Their signal, and it's called a side channel attack because what you're doing is basically like listening at the door to see if you can hear somebody on the other side instead of just knocking and asking, are you home? Right? So they're listening to the door and they're like, oh, do I hear a noise? Maybe is that the cat? Is that the dog? Or is that a person? Right? They only hear this like thing faintly and they're using it as evidence of something else. So that's consistent enough on a real CPU to basically cause a worldwide freakout. Because that's what it did. So I think, and that's exactly the code that line came straight from that code. Theirs is a little bit different. And what they do is pretty cool. They basically let you tune a cutoff because they're trying to detect if something is in cache or out, not just measure it. So they say, okay, if you're under a certain amount of time it took to read this byte, then you're in cache. I'll chalk one up for me. If you're slower, you're not in cache, I won't chalk one up. And then eventually it uses that distinction to say in cache out. So if you're interested in playing with this stuff, all the code's out there online. I'll send the links around. If you want to run it on your CPU and play with it, you can. I noticed that it's a little bit harder to get right on a laptop because of the power scaling. But if I plugged it in, if I plugged my laptop in, I could start to see the differences again. On battery, it's all too slow. At least that was my hypothesis. Yeah.
Our DTSCP is an x86 intrinsic, right?
Yeah.
So it won't work on those.
That's my next plan is to put it on either ARM of some kind. Yeah.
Okay.
Yeah. There's an equivalent instruction on ARM. It's just not that. Yeah. Because I do want to check. I want to play on my M1 and see. Yeah. So you can invite me back and you'll hear about that then. And be like, now I really know. Just get the pizza and leave. So I'm happy to take any other questions, but that's all I got. So I hope you enjoyed it. I don't really care if you enjoyed it. I mean, I do, but I got a lot out of it. I had fun doing it. So yeah, I was like really excited. I was like, I don't know what, and then I got like going down this path and I was like, this is fun. Like, this is exciting. Yeah. So there you go. So get more pizza and ask me questions if you want, or ask each other questions because you probably know the answers too. I just did it for fun. Yeah, I just did it. I know that sounds crazy, but I just did it for fun. It made it easier because I knew I was going to come here and give this presentation to make time for it, but I really just did it for fun. Yeah.
Would like the cache, like timing functionality, would that change if based on the instructions you run? Would like SIFI change how a cache, like how much aligned to the tree?
Yeah, that's interesting. I don't know. I don't know. Like, I think what, so you're saying like, if I was using a SIMD instruction, would it go prefetch more?
Right.
Or would it, yeah, because you knew it was going to do more?
Right.
That's a good question.
More data.
Yeah, I don't know. I don't know. Because I know there's bigger registers than 64 bytes.
Right.
Like I could fetch into a 128 byte register, right? Like XMM.
Yeah.
So would it fill 2 lines up? Maybe. Yeah, I don't know. It's a good question. All right. Thanks. That was fun. Yeah. Do you want me to end the meeting or?
Do we have any questions?
Oh yeah, before he stops recording. Oh yeah, sorry. Oh yeah, I'll send it to, I'm gonna get on your Discord tonight. I don't know, I'm not already on the Discord for ACM.
Yes.
And then I'll send it out. Is that okay? Yeah, just give me a chance to get back to my office and I'll send it. Yeah.
If you have no more questions, I guess we can,
Yeah,
we'll end the meeting.
that's fine, yeah.
Yeah.
I don't have to leave either. I just didn't know if you. Oh, what did I just clicked leave. I didn't, oh, that's because that's my laptop. Sorry.
Yeah.
I was like, wait a second. Yeah, there you go.
It's still on the.
So who's taking classes this semester? Or who's a co-op? Is anybody co-op besides? Where are you at?
I'm a mechanical engineering, so I'm in the fat manufacturing class.
Oh, cool. Very cool. What are you making?
Valves.
What is it?
Valves.
Wells?
Valves. VALVES.
VEN.
Valves.
Yeah,
Jeez.
valves.
It wasn't, I just couldn't hear it. That's the second time. Like, I couldn't hear you either. You're right there. It must be getting, yeah. Now I understand. Okay. That's cool. And what about, somebody over here was in co-op, right? Where are you at? Okay. Like aviation or? Oh, that's cool. Which engine are you working on?
I'm working on the E program.
That's cool. Oh, that's for jet engines or for turbine, for like wind and like their other engines? I only fly in jets with GE engines on them. Rolls Royce? No. Those don't even exist. Yeah. No, not interested. Have you been following that story about the guy they arrested who was a spy? GE Aviation. No, he yeah. It's like a big international headline, but it's so yeah, I experienced
I brought his line, they were used for the project line demonstration and qualification. So like you use that to then get.
it's just remind you of how important this stuff is. How advanced it is.
It's not somewhere horrible.
Thanks for having me.
Oh, thanks
That was
for
fun.
coming. Yes.
Yeah.
It was amazing.
It was a great
It
meeting.
was an amazing presentation.
What, now is yours Revolution UC?
Yes.
Not Make UC.
Yeah, make you see is Jaren's team.
That's right, yeah.
Yeah. All right.
And Cat too, right?
Yeah, Cat too.
Cat.
Yes.
Is Arnov helping again this year or no?
Yeah, he's vice president.
Vice president, okay.
So if he's not helping,
Yeah, right, yeah, you're not, yeah. What are you, Arnov, what are you doing here? You just like warm body? Like, come on.
Yeah, so I don't know.
I signed up to judge, so
Yeah.
I judged last year, it was fun.
Guys, they put pizza if you guys want. Pepperoni is okay.
All right. We end a meeting here. Thank you guys. Let me just stop the recording.